Hi everyone, welcome back to day 2 of our daily study group following Etienne Bernard's wonderful book Introduction to Machine Learning. A quick thank you to everyone who completed the survey yesterday. We very much appreciate your feedback. I was just going through, I managed to quickly skim through most of the responses to the question, what are you looking for in this study group? Majority of you responded with, an overview of machine learning, also getting to know about Wolfram language functions, and that's exactly what we are hoping to provide in this study group, hoping to learn about as we go through the first 6 chapters of Etienne Bernard's book. And then I did have a few responses talking about very specific projects. Well, thank you for sharing those ideas. I'm not sure how much we'll be able to address the specific needs of the project, but I do hope that you get inspiration about what sort of machine learning you want to do, or other things that you could use in pre-processing your data or working with your data before you jump into machine learning. Some tips and tricks about which sort of algorithm, which machine learning paradigm you want to use. If you do have related questions about your project, I would always encourage you to post on your on the community thread here. I already see some posts there, very encouraging. Thank you for sharing your thoughts as you read through the chapter. I would encourage the others to post questions there as well. There's one other feedback I received. Some of you were looking for formal understanding of the theories and algorithms, or the math behind machine learning. So I have to say that is a little bit beyond the scope of this study group. We can, spend semester-long courses trying to understand machine learning. This study group, this book is meant to be a very quick and broad overview so that you can, jump right in. You get an understanding and you jump right in. And what is great about having Wolfram language as a tool to learn about machine learning as you read through the book is, as I've shown, and we've done this yesterday, we have the code right here. So, it's a very hands-on approach to learning about machine learning. I mean, you could talk theoretically about things like, confusion matrix and all, but here you have a chance to just run the code and see exactly what it looks like, tweak the data a little bit and see how things change. So again, a very hands-on approach, very application-oriented approach in the study group in the book. So for the formal understanding of the theories, or the deeper dive into the algorithms that we will be using, that Classifier uses under the hood, that will have to be a topic for another course or another study group. All right, so let's start today with actually a very important question, and that is, do you have access to Mathematica, and are you able to open Wolfram notebooks? Because if you do, then you should be able to, go to the landing page of the course, and you should be able to download either notebooks for the entire chapters or just the code, so you can play around with the code. And I think that will really, really help your understanding of the book, and the code, especially how you can use Wolfram language code. So what I've received so far, 81% do have access to Mathematica and are able to open notebooks, but 19% do not have access. So for those, I would quickly share this link where it should pop up on your screen, and you can check access to Wolfram products available through your organization. It'll take you to a page where you can add your organizational email, and it will let you know whether or not there is a site license for Mathematica at your organization. And that will be a great way to get started using Wolfram products. And if you do not have site license, you can always go for the trial license. We have a 15-day trial, and that would be a great way to try out notebooks, try out machine learning functionality. Having that important question out of the way, let's do a quick review of what we learned yesterday. So we talked about, generally about what is machine learning, and we did also talk about the major machine learning paradigms. We talked about supervised learning, unsupervised learning. The third paradigm was reinforcement learning, which we are not going to cover. I saw someone was disappointed in their survey response that we are not covering reinforcement learning. So a quick question about supervised learning. So I'm looking for the odd one out here. Among the answer options, can you pick the one that is not an example of supervised learning? Remember, supervised learning is where you want to have labels. Supervise, the term supervise is referring to some sort of supervision where, an expert has supervised the data set and has added his expert knowledge, has added labels, whether they are like text labels, dog, cat, day, night, spam, not spam, or numeric attributes, price of a home, weight of a person, number of runs scored by the baseball player, things like that. So you cannot do supervised learning unless you have labels. Okay, so text generation seems to be getting the highest number of votes as being not an example of supervised learning. That's a weird sentence, but anyway. Well, it turns out the right option in this case is anomaly detection. So classification, definitely trying to predict class labels, A or B, dog or cat, spam, not spam, is a supervised learning task. Regression is also a supervised learning task where you have to predict a number, inches of rainfall, runs scored by the player, price of a home, and so on. So you have to have training data that has these labels, has these numeric attributes. You have to have training data with the price of the home in order to be able to create a model which, when given certain characteristics of a home, will then be able to predict the price. So that is also supervised learning. Text generation. So that's the tricky one here. It seems like if I want to generate text, for example, if I say the sentence, the cat sat on the, and you want your model to come up with mat, it seems like where is the label? But turns out that this model had to actually be trained on a lot of data where the label was the completion. So the model was trained and it was given these sentences. There was a lot of pre-processing involved, but it was kind of, the label was what do you use to complete the sentence, and it has seen lots of those examples, and that is why now when you ask it to generate new text, it is able to come up with this completion. So generation, although on the face of it, when you're using it, seems like, well, where is the label? It is a case of supervised learning. What is not supervised learning is anomaly detection. So anomaly detection is where you have a lot of data and then you want to find the outlier. You want to find the anomaly, what is weird. So then you don't really care about the labels. You just have the unlabeled data. You include all the features or attributes you have in that data, and based on all the features and attributes, you just try to organize your data and see which samples are the odd ones out that don't really fit neatly into any category. So then let's talk about unsupervised learning. Can you now pick the option that is not an example of unsupervised learning? Again, I'm looking for the odd one out. So 3 of these are examples of unsupervised learning. One is an example, one isn't unsupervised learning. So unsupervised learning, where we don't care about labels, class labels. We don't need we don't need to hire an expert to label our training data. We can just, pluck off unlabeled data from the wild and work with it. All right. So let me go and share the responses received so far. Image identification wins with 50% of your votes, and that is indeed the example that is not unsupervised learning but supervised learning. We've seen examples in yesterday's session from the first chapter. Image identify, the chapter opens with image identify. The only reason the image identify function is able to look at an image and say, oh, this is a parrot or this is a giraffe, is because the model was created by showing lots and lots of images which were labeled by a human expert. Clustering is just organizing your data samples to see in kind of groups each sample falls in. And dimensionality reduction is, again, we don't need labels. You can just start off with any number of attributes or features of a sample. What you're trying to do is reduce the number of features, either for interpretability or for visualization, easy visualization. So feature space plot in Wolfram Language is something that automatically does dimensionality reductions. You don't care about labels. Whatever attributes you have, numbers, text, images, you just mathematically, computationally process those attributes and try to get them down to fewer number of attributes. Missing value synthesis, again, you don't really need supervised learning. You don't need labels. What you can do is, there are many ways to do this. You can, go with, you can replace the missing value with maybe the mean of the entire data set, the median, or the mean according to the class for that entire data set, if you do have labeled samples. So you can work with the unlabeled data to somehow derive a distribution of that value from the data itself. And we have Wolfram language functions like learn distribution that can do this. So the only option here that is not unsupervised learning is image identification. All right, thank you for those responses. And here's the last of the review questions. So you must have heard of natural language processing. It's everywhere these days, right? Which machine learning paradigm do you think we can use for natural language processing? It's kind of an open-ended question. And I'm happy to say there is no, specifically right or wrong answer. But I'm curious to see, based on what we covered yesterday, or at least reading through the first two chapters, when you are thinking about working with the natural language like English, or just text, speech, things like that, which way would you lean? Would you lean towards using supervised learning, unsupervised learning? Do you think both have to be used? Fantastic. I was going for the fourth option. 71% of you have picked either can be used depending on the task. And this really speaks to the broader application of machine learning. It's a very task-based application area. I think you should never jump into a project or a data set thinking, oh, I am going to use classification or regression or clustering or anomaly detection. It always is the choice of algorithm, the choice of machine learning paradigm definitely depends on what task, what question you are trying to answer. So with natural language processing, there can be supervised learning, like, text generation, text translation. There can be unsupervised learning when you're trying to extract features from the text. What are the useful features from the text? So something like dimensionality reduction, that will be uh, unsupervised learning. Do you have to use both? Maybe not. If you're only curious about the features, then you need to use supervised learning. So um, I, I I think the last option makes most sense in this context. All right, so then as we jump into the session, this is an extremely important question. Let's do a quick poll to see how many were able to read chapter 3 on classification. And again, this is just a group of people interested in learning more about machine learning. So we have not assigned homework. It was our recommendation that you read the chapter. If you didn't find time to read it, that's absolutely okay. I do hope attending the live session helps out somewhat. We'll try to go through some of the code. We'll discuss some of the important points. Now, given the uh, time constraint, I would not be able to go into uh, all the details covered in the chapter, and I do hope I can encourage you to go back and read through the chapter. If you have any further questions as you are reading through the chapter on stuff that we are not able to cover today, please do post them on community, anything specific. And we are looking at it, and your other study group members are looking at it. The broader community of Wolfram users are looking at it. So that's a great place to have your question answered. So it seems like this is kind of incredible. We have an exactly 50-50 split between the yeses and the nos. Oh, the nos win. Okay. All right. So my plan is to kind of go through the code mostly, not as much through the text details in this particular chapter. So let's jump right in to classification. I like to always think of classification as a way to answer the question, is this A or B, right? So in this first example, right, we have a really, really simple task. We have the weight of the vehicle, and based on the weight, we have to decide whether this is a car or a truck. Now, this is really simple because we have just one feature, and we just know that, trucks are bigger, so it makes sense that the higher the weight, that would be a truck. Easy way to visualize this, and you'll often see visualizations being used for exploratory data analysis. It gives us an intuitive understanding of the data. Now, of course, in this really simple case, it doesn't add too much to our understanding, but we can see the cars are here towards the lower end of the number line, with less weight here, and the trucks are over here. Now we could use our little classify function. I will definitely encourage you to look into the documentation for classify. It's incredibly detailed, and you will see here one of the most important things is how you can have the training data structured. So classification is supervised learning. We have to have labels. So the labels are represented by the outs here, the out one. You can either have your sample and its label, sample 2, label 2, in this way, a list of rules between input and output, or you can have all the samples in a list, and they are pointing to all the labels in a list. Okay. And then you can have the lists, like each list is one sample, and you can say, oh, by the way, the nth element in the list is the output, right? So you can either change the label to the first element or the second element, and so on. Then you're also actually able to use data sets, which are a nice, convenient way to represent structured data in Wolfram language as input to the classify function. So here you see we have this first form here, in out. So we have the input, the feature, and the output is the label, right? So we have the list of rules, we feed it into classify, and we run it, we will get the classifier function here. I've named it C. You can name it whatever you want. You can name it car, truck, classifier, whatever. It's just a symbol, a variable that will hold the classifier function. And then I can use that on a new input, say a vehicle whose weight is just 1.6. I believe it's in tons. No. So it says, okay, this is a car. And if I give it 4.2, it says, okay, this is a truck. And now in this picture here, we are adding some new inputs. One is right here, here, and okay, we just have two, right? One with 1.6 and one with 4.2. Now, if you're working with this notebook and you see these little boxes here and you're wondering what on earth is that? What is it doing? So this is an iconized version of code in the notebook. The idea is that, as the reader, I would like you to focus on the important part of the code. The important part of the code is the data points that are going on the number line, that you're plotting on the number line. The rest of the stuff here is to make it look pretty. So I can go ahead and uniconize, click the little plus icon and uniconize it. There's a lot of stuff in there because given a wonderful visualization of functionality, we can go a bit crazy in customizing our pictures. We don't always like the default maybe, and so we have very specific ideas about colors and schemes, so we can put all of that in here. But when you're putting it in a notebook, you really don't care um, whether you're whether you have 0.03 size points or whether you have written it as car examples, truck examples, so you don't care about that. So what you can do is select all of that and go and iconize your selection, and that's kind of hidden out, so your reader is not distracted. Okay, so let's see, 2.7 here. No, so this was 1.6 and 4.2. But now if you had a slightly ambiguous data point, 2.7, that would be somewhere here, right? We've seen the cars are on the left, the trucks are on the right. What do we do with 2.7? Well, for the model that we have created with just these few data points, it says, well, 2.7, I think it's a car, but how confident is it? So then we want to check what was the probability actually it assigned to this sample being a car or a truck. And so this is another way of using the classifier function. You can either just ask for the decision, give the input, and it'll give you the decision, or you can ask for the probabilities. And if you run this with probabilities in quote here, it says, okay, I am 0.6. My probability of certainty that this is a car is 0.6, whereas for truck, I'm only 0.3 or 30% sure. Whereas for the obvious case where it was 1.6 and it was pretty certain that it was a car, you see the probabilities clearly show that. So it had a probability of 0.99 that this was a car and only 0.00023 that this was a truck. So sometimes you want to see how confident the classifier is uh, about the decision that it is trying to give you. The class probabilities kind of can be interpreted as the belief of the classifier. Okay. Let's take a quick look at questions so far. Thank you, Luke, for taking care of all those questions. All right. I don't see any further new questions remaining here. So now we will jump over to a classic machine learning data set. It's slightly morbid in my opinion, but you will run into this data set no matter what programming language you're using for machine learning. It's the classic hello world of machine learning. So turns out this data set is based on the class, age, and sex of passengers on the unfortunate ship, the Titanic, and it has also information about whether this passenger survived or died in the accident, in the shipwreck of the Titanic. So it has, as you can see right away here, that it has 4 attributes. Right? I'm not saying any one of this is a label right away, because what you use as a label will depend on what you're trying to predict. Okay, so if I would like to predict whether a passenger survived or perished, then survival status would be my class label, and these would be my attributes or features in my data set. So I can have a feature like what was the class in which they were traveling, what was their age, and what was their sex. So this is representative. This row here is representative of a passenger, was 48-year-old, was a female, and was traveling in first class. And since we know they evacuated the passengers, the first class passengers, the younger passengers, and the female passengers earlier, this person seems to have survived. Okay, now looking at the code here, taking it apart a little bit. So seed random here, what seed random is doing, and we can uniconize, and we see that that says basically seed random 12. Why do we care about this in machine learning? Because we are randomizing the samples. If I did not use seed random 12, that's like I'm seeding the random pseudo-random generator, pseudo-random number generator and on my system. If I did not seed it, every time I ran random sample, I would get a different set, and that probably is not what you would want to see. I want to see across all systems, I want to see the same sample set generated. Just makes it easier. Okay, and if you want, so as I showed you yesterday, and this is something I use all the time, I try to take apart the code and I try to figure out what is going on inside. So here, if you triple click on resource data, you can copy it out and you can paste it somewhere in your notebook and run it. You will see it gives you the entire data set with 13,009 rows. And resource data is a way, as you can look at the documentation, is a way of downloading data resources from the Wolfram data repository. So here on the Wolfram data repository, we have all different types of data set, and you can browse either by categories or the type of data, whether you're looking for numeric data, text data, and so on. You see, you can browse these, and what's great is you can, get into it. So maybe let's get into um, 2015 Chicago Marathon data. I haven't seen that before. So if you go to the page for that particular data set, you will have all this example code that shows you how you can download the data and how you can work with the data. In fact, you'll have examples of visualization and analysis, and all you need to do is really just copy it over, and then you can go ahead and use that in your notebook. So one of the data resources there is the Titanic survival. In fact, what I can do is I can go in and search for that data just to see whether is there in the repository, and see here there's the sample data. It says Titanic survival, and it shows you how I can go ahead and use this data set. In fact, it has an example with classify. All right. If I just did a random sample of the data set, what it would do is just it would shuffle the data and give me just this data set shuffled up. I would still get back 13,009 rows. What the rest of it is doing, okay, this here is just trying to make it look pretty, because here you see I would have gotten 20 rows at a time. That's the default when data sets are shown. It decides based on the number of items you have in the data set, and in this case it chose to show me 20 rows, but for the optics of the book itself, I think they wanted just 8 rows, and that's all it is doing. Nothing to do with machine learning. I just talked about it in case you were curious, what is this rest of the code doing? But we'll stick with the code in the book, and then we'll have this data set here, right? Now we are going to do something really, really useful. We want to do some exploratory data analysis. So firstly, we can find out the length of the data set. We can already see it here. So that's one of the advantages of having things represented in a data set. There are 13,000 and so rows, but I can also just use the length function in Wolfram Language. Says, okay, 1309. I can then also use the count function to find how many samples have the age attribute as missing. You can see these here, one example where you have the age attribute missing, and so you would like to figure out how many of those samples you have that have the missing attributes. So I can just pick this out, and I'm using pattern matching here. I'm trying to find the missing element. Now this is a nicely formatted, curated, clean data set because I got it from the data repository. That's one of the conveniences you have for getting data resources from the repository. Somebody has taken care of them, and you don't have to worry about dealing with weird characters, weird missing data. We accept there is missing data, but it has been consistently formatted as missing object. And so if I run something like this, the count function with the pattern missing, I get a count of all the data samples. So 263 out of 1309 have the age attribute missing, right? And I could do something like the fraction to find the fraction of samples. Now, in Wolfram language, it tries to keep it as accurate as possible. So the result is sometimes returned, oh, all the time is returned as a symbolic answer. And so what you can do is you can convert it to the numeric form using the n function. And now you get something that is more um, useful or interpretable. Okay, beyond just exploring how many samples actually have the missing data, 263 is not bad. And one great thing about Wolfram language functions is that if you have represented it in the right way, functions like classify, cluster, find clusters, they can just deal with missing data. You don't have to worry about taking them out of your data set. Just represent these missing samples or missing attributes correctly, consistently using the right form. So using the missing form is the best. And so they can just work with the missing data. So then what we can do is we can look at visualize the age. Let's see. So let's pull this out. This is a way of getting one column out of the data set, right? Titanic data here is that entire data set. Now, if we want to pull out just one column, we say, give me all the rows of the column age, because age is the name of the column, right? And this will give me all the ages, right? So what do I do with it all? I can feed it into histogram. And histogram with all its default option will create a histogram. But maybe I want to be very specific. As we saw, we tend to go a little crazy with exactly how we want the picture to appear. So we can, specify what the image size should be. Should it have frame? Should it have a frame label? This I can get behind. I hate visualizations where there are no axis labels. And so this was important. We wanted to say, okay, this is the age and this is the number of people of that age group. And we have a better histogram, but we can see how the age is varying. And if I remember correctly, Etienne talks about it, that why this is important. Um, you know, it sees that the first thing to notice that, okay, we saw that 20% missing values in age, but the second thing that we see is everything looks fine. We don't have any negative ages, which would be problematic, or exceedingly high ages, and the data does not seem long-tailed or spanning many order of magnitude. So that is great. The next exploratory analysis we could do is see how much or what fraction of our samples had a specific attribute. So we can see here that, 466 of the passengers were female, at least in our data set here. 843 were male. Same breakup by class, survived and died. You could have done this with a bar chart as well. So if I just pull this out, okay, the hash here is part of the pure function, right? So what I could do is I could either, say, oh, give me the counts um, for this, and then I would get female and male. I would have to keep on copy pasting and say, okay, now I want it for class, right? Or I could make this into a pure function with the placeholder, and I put the ampersand sign to complete the pure function, and I map it over a number of different column names here. And so I get the counts for sex, I get the counts for class, I get the counts for survival status. So that's just a quick way of doing this. Why be satisfied with just the numbers? I can create the visualization here. Right, so I get the 3 different pie charts. Now this is of course with just default. Here is where all the details reside about what sort of chart labels you want to use, what sort of plot label you want to use, and so on. So I mentioned that we could have easily created bar charts with the same data, right? But when you have this specific, the attribute can be of a specific type or the other. It's a nominal or categorical attribute, so it can only belong to certain categories. It makes sense to visualize what fraction of the entire data set has that particular attribute. With this visualization, you can see there are more males than females, but it doesn't give you this idea of like, oh, that the what fraction of your data set belongs to one category or other. So depending upon what you are interested in looking for in the exploratory data analysis phase, you can use one or the other. All right. And then we jump into using Classify, which is the meat of the chapter here. So the way this has been done is first you pull out the feature attributes, because survival status is going to be the label. So you pull out the feature attribute and then you make it look like a nice pretty data set. And as you saw in the documentation, the classify function can use a list of rules, can use an association, can use a data set as an input, and it is really up to you how you want to format your input. You don't have to have a data set if that isn't something you really care about. So let's go back to classify. If this makes more sense to you, having the input output pairs, go for it. Personally, I find this easier to understand, or sometimes this one, and I don't often end up using data sets, which is fine, right? So here we have all the features in a data set, and then we have all the labels in the data set, and so we are going ahead and using here, ignore this for a moment. This is what you will find in the notebook. Okay, we are pointing features to classes, so we are doing this format here, features to classes, even though they are in dataset format. Okay, dataset is just like a wrapper, so internally it is really a list of uh, internally it's a list. So in fact you can see that here. So if you do features normal, you can see it's a list of associations here. So class is first, age is so and so, and then you have a list of all these associations. Okay, so you can go ahead and say, okay, features to classes, and you're very specific. You want to use random forest, and again you can find out what are the methods available. Let's see, method. With classify. Okay, I know we have a listing of the methods. Let's just try to find that. Sorry for all the scrolling. I'm just trying to get to method. Oh, here you go. So we can use decision tree, gradient boosted trees, logistic regression, Markov, naive Bayes, and so on. Again, responding to your survey feedback, I think there are folks who really want to understand the algorithms that are being used for classification. That is beyond the scope of this study group. So this is meant to be more practical, hands-on, and these are already available. People have worked on it, and especially here in Wolfram Language, having a super function like classify, it has been implemented as efficiently as possible and encapsulated for ease of use. So you go ahead and use classify. If you do not provide the method, it will automatically pick the method that is most suitable for your data set. Or if you have a pretty strong opinion about what sort of a method you want to use, you can specify it, right? Like the one here. And there are other properties that also you can specify for your classifier model. Here I have time goal, which, how long the classifier should be trained. And so I can either run this, and then once you have run it, you have the classifier model here, and you can give it a sample class, right? Where a sample a data point where the class is okay, this is a little confusing. Class as in the class of the passenger on the Titanic, first class, second class, or third class. You have their age, as 20-year and the sex set as female, and you want to find out the probabilities of whether this person survived or died. I wanted to show you an alternate use of classify with a data set, especially when you have something like this. What you can do is you have the data set or the variable that has the data set, and you can actually just specify the column name. But note, this is the entire data set that has all the columns, including survival status. Features here has pulled out just the features from the entire data set, class, age, and sex. And survival or classes here has pulled out the survival status column. Titanic data has all 4 columns. And what I'm saying is you can just set the column which you want to be used as the label in this way. And this can also create a classifier for you. Okay. And so then the rest of the code we have, we can look at the probabilities. So here using the classifier created in this way, I get a different classifier for sure because I did not specify the method. And so it was just using randomly a different data set to train and try all the different methods. What I am interested in seeing is what method it picked by default. And so I can do something like this, use information to find out more about my classifier. And so now it seems that by default, when I did not specify what method to use, my model used nearest neighbors and came up with an accuracy of 77%. And this is what its learning curve looked like. Okay, one thing I do want to point out in this chapter, I hope you got to it. And this is a newer addition to our classify function, the ability to find out more about a feature and what effect it has on the decision. In fact, kind of like an importance value for the feature. How important is it, that particular feature, in predicting the class of your example? So one popular way is the SHAP values, which stands for Shapley Additive Explanation. And we have that available built into the classify function. So you can end up and you can use something like this where you say, okay, my classifier model here, let's just use it here. Sure, it's SHAP values is here. Oh, where is it? Oh, there you go. So just like you can ask for probabilities, you can also ask for SHAP values, and then you can say for the survived class, and you can see that gender played a very important role, and age apparently didn't seem to play that great a role in determining whether a passenger survived or perished. So this is explained in this section of the chapter, right before you move on to the example with topic classification. Okay, so I've shown you how you can find more information about the classifier using the information function. And one helpful thing with information is you can directly get like a nice report of all the details about the classifier, or you can ask for specific types of information. So I can say learning curve, and it will pull out the learning curve. And as Etienne explains here in this last part of the section, a learning curve would be a nice, useful piece of information to look at if you want to decide whether, you see here on the x-axis we have the number of training examples used. So if you want to decide whether adding more data to your training will help improve the performance of the classifier, you can look at the learning curve and see how it changes as more and more samples were used in building the model. When you used a few samples, you were doing really badly, and then you were here with 200 samples and then moving up to 1000 samples, it's not that great of an improvement. So you're fine with fewer samples in this case. Perhaps adding more and more samples will not contribute to the performance of the classifier. But there are definitely cases where having more samples, more representative samples that represent the variety of real world occurrences of a particular phenomena, when you have more of those samples, the performance of your classifier can definitely increase. Okay. So I don't have time to go through the topic classification code, but I did want to point out some interesting things that I found personally interesting. Is for the topic classification example, we just downloaded Wikipedia articles on the topics of physics, biology, and mathematics, and I found this very interesting here that Etienne mentions that we create this data set in a very quick and dirty way, right? We get the articles, we break them into sentences, and then we assume that every sentence on a page is talking about the main topic of the page. And this is not always true. The math page can have topics that, sentences that talk about physics. But then he makes the observation here that, um, do not get carried away by the idea of like cleaning your data set. You don't want to sanitize it to the extent that it is not representative of the real world. And that can be problematic because your data will not represent the diversity that you actually see in the real world. In fact, there are major issues, ethical issues about using machine learning, especially when machine learning models do not represent the diversity in the real world and they can be biased toward one class or other. So it's really important that you have a balanced data set. It's representative of both types of classes or more than two classes, in which case you want to have a nice representation from all the classes. And here also there is an example of EDA, which is not necessarily beautiful pictures. So when you have data sets where it's not really possible to quickly make a nice pretty picture, something like this works great for EDA. Just randomly look at some of the inputs you have created, a random choice of the sentences and the topic, and you run it again and again. This is random choice, so you run it again and again. You can see the different types of inputs. So that works great for exploratory data analysis. So the last topic that I would like to cover that is kind of important is classifier measurements. So we saw importance, information that gives us more details about the classifier model, but to decide whether or not the classifier is actually performing well, we want to look at classifier measurements, which is when we apply the classifier to a test data set. The classifier measurements is introduced here towards the end of this example, the topic example here. You can see this has been run on a test set, and now here we see classifier measurements. Among different performance metrics available through classifier measurements, we have accuracy, we have the confusion matrix, which kind of shows you how many samples that actually belong to this class were correctly classified as belonging to that class, how many samples that belong to the class biology were incorrectly classified as mathematics or physics. So the confusion matrix is a great way to quickly get an understanding of how well your classifier is performing. Beyond confusion matrix, right at the bottom section here, in this chapter, in the section that says, see, in classification measures section, beyond accuracy, which is again a decision-based measure, which as the word suggests, really just tries to check the fraction of test examples that were correctly classified. There are two useful measures. One is precision, because sometimes accuracy is not really helpful in telling us how well the classifier is performing. So precision is an important measure which really tells us the fraction of correct classification amongst all examples, right? Of all the examples that were, for example, classified as biology, how many were indeed biology? And we can see here the precision was 0.75. Of all the examples that were classified as mathematics, how many were indeed mathematics? So that might be a measure that you might be interested in. Or there is also recall, where you're interested in the fraction of class examples that are correctly classified. So, sorry, I made a mistake there. I'm so sorry. I was talking about recall, right? So the fraction of biology examples that were correctly classified as biology is recall, and the fraction of correct classification of all the examples that were classified as biology, how many were indeed biology, that is precision. I do mix it up sometimes, and if you're new to machine learning, it can be a little confusing, but I hope you just sit down with the text for a little bit and look through it. It will make sense. And so sometimes you might be interested in one and not the other. I think I have a poll question that might make this a little clearer, and I will use that in just a little bit. Okay, and the final topic I want to end with is actually from the previous chapter. I think it's at the end of the previous chapter. Great, you have all these performance metrics that you can use to assess how well your classifier is performing. That's wonderful, but at the end of the day, you realize your classifier is not doing great. So what can you do? Not cooperating with me. I'm trying to get to the end of the chapter here. Okay, I apologize. I can't seem to find where Etienne is talking about it. But I did want to mention that it's really important to pay attention to a couple of things to improve the performance of your classifier. Obviously, if you can add more data, and we've seen that in the learning curve in our examples here, when we look at the learning curve for the topic classification, we see that it when you add more and more examples, initially the performance definitely improves a lot, but as you go towards the end, it kind of plateaus. So not always adding more examples will be helpful. Adding diverse examples from across different classes, that is helpful. And then you could pre-process your data, or you could tweak things that you could use with the classify function. You could tweak the type of method you want to use, and you can play around with the parameters of that algorithm. As you can see, a specific method has options for tweaking the method parameters, in this case feature fraction, leaf size, tree number. All of those values are specific to the random forest algorithm. So if you have an understanding of the algorithm, you can go ahead and tweak these parameters and try to improve the performance of your classifier. However, for a beginner, Classify does a great job of automatically selecting these parameter values. It just works through the training data. It uses batches of the training data to train a classifier, tweak those hyperparameters, and see whether or not the performance is improving. And it will pick those values for you. So if you have no idea what method should be used, let alone what parameter values should be used, that's absolutely fine. Classify can do that, and that's really the special advantage that it is bringing to the table, that it's very easy to use classify or predict in Wolfram language and jump right into machine learning. Right, so I think I'm going to go ahead and stop there today. I'm sure there are lots more questions that you might have. I would welcome those questions on the community thread for this study group, but let's wrap up with some quick poll questions to review some of the topics we discussed today, starting out really simple. We talked about classification today, so what sort of question do you think you can use classification to answer? So yes, is this A or B, where A or B is the class label. That is what classification would try to answer. How much or how many is regression. So if you have a numeric attribute that you're trying to predict, that would be a question that you can answer with the help of regression, and the Wolfram language function for that is predict. That's what we'll be looking at tomorrow. How is the data organized? Something like clustering, unsupervised learning, find clusters in Wolfram language, that might be used for that. Is something weird, out of ordinary, is kind of like what is the anomaly in the data set, anomaly detection, and we have other Wolfram language functions for that. So classification would answer a question of the type, is this A or B or C or D or E? And along the same lines, which of the following is a requirement to be able to use classification? What must you absolutely have in your data set to be able to use classification? Okay, so there's a bit of a split between data samples must have nominal categorical features, or data samples must have categorical class labels. Now, I will agree if you're thinking that, hey, if there is a categorical feature, I have the potential of using that feature as a label. If that's what you were thinking when you picked this, that's fine. But given I've used the term label here, a label is incredibly important for uh, using classification. So I would go with the answer here. Data samples must have categorical class label. Potential labels, yes. A categorical feature that could be potentially used as a label, yes. But having that label is important. As far as features are concerned, they can be numeric, they can be nominal, categorical, I don't care. I can just have numeric features and have a class label. I can have a mix of numeric and categorical features and still have a class label. So the label is much more important than what type of features I must have in order to do classification. This is an interesting one. EDA is my favorite stage of a machine learning workflow. And sometimes I get a little too carried away with exploratory data analysis and spend an insane amount of time there, and which causes a lot of problems. But it's, you can't deny it's very important. But the question is, can you do machine learning without exploratory data analysis? True or false? I mean, Etienne clearly speaks highly about exploratory data analysis in this chapter. And we see some really cool examples with the simple Titanic dataset, the pie charts, the histogram. And so 64% of you have picked you can do machine learning without exploratory data analysis, and that is indeed true. Whether or not you do it, that's a different matter. Okay, so I hope this question, something weird happened there. Okay, I hope the question has popped up on your screen right now. Will help you think through the metrics we talked about, the performance metrics for measuring the performance of a classifier. So there's accuracy, right? How many class labels you got right, one class or the other. So in this case, you're trying to classify emails as spam or not spam. How many you got right, you have accuracy. With precision, you can, as we discussed, you can have the fraction of correct classification amongst all examples. And when recall, you can have fraction of class examples that are correctly classified. So if you're trying to answer, out of all the emails flagged as spam, what proportion were actually spam? Which measure are you really interested in? And with 50% of the votes coming in favor of precision, that indeed is the right option. So you have all these emails that were flagged as spam. How many of them, how precise was your classifier? How many were indeed spam? That's precision. The recall would be, of all the spam emails, how many were correctly classified as spam? All right, and the last question, I have for you is improving the performance of a classifier. Just wanted to review that topic one more time. What are the different ways you can improve the performance of a classifier? And as you answer that question, thank you so much, Luke, for taking care of the Q&A pane. Thank you for all the questions you've been um, adding. I hope it seems like Luke got to almost all of them, except for one or two that just came in. And that's it for today. Tomorrow we are going to talk about regression. So if you have a chance, please try to go through the chapter on regression. And we are going to talk about the predict function in Wolfram language that you can use for regression. And again, I'll try to go through some of the code. If you have any specific requests for, specific part of the code, please feel free to bring that question to the session and we can focus on that particular code. Or if you're interested in any of the end of chapter exercises, maybe pick one of those and bring them and we can try to work on them as well. If I don't manage to do it in the session itself, I would definitely try to post a response on the community thread. All right, so yep, all of the above, right? You can use more examples, you can use different types of example, you can use better data pre-processing. Although the model is created automatically, especially if you're using a high-level Wolfram language function like classify, where the model is automatically making some selections, you can definitely work with the model, you can tweak the model, you can rerun it on newer data sets, and you do have an incredible amount of control if you try to set out and improve the performance of the classifier.